In the previous video, we looked at the code and stack segments of memory, where we store code and local variables for functions. In this video, we'll look at global and dynamic memory. If we assign a variable outside of main, then it is a global variable that exists everywhere. That is, we can access Z in both the main method and the sum function. We can't store global variables in the stack because the stack only contains variables that have been defined for a certain function. So it turns out that global variables are stored in their own global variable segment right below the code segment. Unlike the stack and its stack frames, the global variables are not connected to any particular function. That way, the variable Z remains allocated for the entire program. But the global data segment doesn't just hold global values. It also holds some other values, such as string literals. While the variable cPointer is allocated on the stack, the value of cPointer is the address where the string hi is stored, and that can't be on the stack. String literals aren't always being assigned to variables after all. So that string, a constant, is also stored in the global data segment, where it can be used anywhere in the code. That leaves one more type of memory, dynamic allocations. malloc, or memory allocation, allows us to allocate memory while the program runs. If we use malloc to create an array with 500 items, where will that array be located? It can't go on the stack frame for sum, since we might want to access the array after sum has returned. Remember that dynamically allocated memory should have a lifetime longer than the function in which it was allocated. All dynamically allocated data is stored right below the global segment in an area called the heap. When we malloc 500 integers, we are reserving 500 integer-sized locations in a single uninterrupted chunk of the heap. Over time, as we malloc more things, the heap will begin to fill up. Whenever we free an allocated piece of memory, it is marked as being available for allocation. And future malloc calls can reallocate some or all of the freed memory. At this point, we have our stack growing up and our heap growing down. Both have a maximum size, so if your program exceeds the maximum size of the stack or heap, your program will encounter an out-of-memory error, or ENOMEM. But wait, there's space in the middle. Why didn't the stack and heap meet? We won't discuss it in detail, but other segments, like a file buffer segment, may be created in the middle. And what about the free space at the bottom of our array? The operating system reserves the largest addresses in memory for its own use. These OS segments cannot be accessed by normal programs. If you do somehow try to address OS memory, you will get something called a segmentation fault, or a seg fault. You've probably already seen a few of these. A seg fault results when we try to access something we don't have access to, or something that does not exist. You can get a seg fault in a few other ways. Remember that the code segment does not start at 0? One of the most common problems is an uninitialized variable or pointer, which results to it pointing to the 0, resulting in a seg fault. 0, or anything close to 0, is used as a buffer for failure.